The steps followed in this video will create from a survey spectrum a set of spectra that are over a narrower energy interval. In this case, we've got a data set that has been compiled as if it were an image data set, where we have VAMAS blocks that contain multiple spectra, and these represent rows of pixels within an image. And what we want to do is pull out from this array of spectra just an interval that's going to be defined by the regions that represents the peak structures and background that are of interest to us. So the entire survey data is not used when we do some kind of calculation. And only VAMAS blocks that have regions defined will be included in the file that's created when you press the Save Regions button on the Regions Property page. So once you've given it a new name, we can then save it and then open the file to reveal the data set that has been created from the regions. So now we have a set of spectra that only focus on the oxygen and the carbon peaks. We can repeat this exercise a second time, and this time we'll do it using a slightly different form of the same data set. We're going to create a data set that contains VAMAS blocks that are based on the AVG conversion filter, and when you use the AVG filter, each VAMAS block corresponds to a spectrum. And so we have many more VAMAS blocks, same number of spectra as it happens, but they are now arranged so that we can see the individual spectra and overlay them as a unit. And again, what we want to do is create a region. So if I Control Tab, I go back to my previous data set that had the region defined, propagate from the one file to the other, and then I know I've got exactly the same region as I had previously, and I can save it again. And once again, I will end up with the number of VAMAS blocks corresponding to the original VAMAS blocks for which a region was defined. Now, the reason that you might want to do this is we've invested a lot of time in collecting these data. Each individual spectrum has an acquisition time, and the signal to noise that one obtains is based on that acquisition time per spectrum. However, principal component analysis will let us treat the entire data set as a single entity, and we can calculate principal components and determine a suitable number of principal components that will represent the signal within these data. So if we select, as you can see here, the 8th abstract factor looks very much like Poisson noise. So if we use 8 abstract factors and we reproduce the spectra using 8 abstract factors, we end up with a smoothed form of the data, and we can compare this against the original form. If we take a copy of these smooth data and then we can display them, one raw data, one process data form, and you can see that the data set is very nicely reproduced by the abstract factors so that we have much better signal to noise. Improving the signal to noise in these data allow you to calculate line shapes from data or component spectra from these data, and then use components that are more representative of the graphene oxide and the reduced graphene oxide, so you can work out the proportions across the sample of these two forms of the material.